Hey folks, so let's talk about bootstrapping. I know I've already kind of talked about this, but sorry, I have to readjust my mouth as a cat because it's not doing what it's supposed to. Weird. Okay, how about, no, I don't want that. My eyes are fine. Okay. Jaw movement. Wow. Cool. Cool. I think this is maybe cool. Oh, no, no. Oh, my mouth is still. There we go. Howdy. Doody. Doo, 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 doo. Okay. Well, this is what we're doing because I'm tired of being a fish, so I'm a cat, and we're going to talk about bootstrapping. And I'm going to start with a data-driven example. So let's talk about rent in Edinburgh because Mina is glorious and I am using her data and code for this example because it's good. But anyway, let's take a guess of how much you think a 3-bedroom flat in Edinburgh rents for. Well, I had no idea. So let's look at a little bit of data. Here are 15 3-bedroom apartments in downtown Scotland that were randomly selected from Rightmove, the website. These are semicolon delineated, hence CSV2, and I've printed some of them out here, and they're in a range of values. But here's our observed sample. The sample mean is almost 2,000 pounds, and my quick and dirty rule for converting from dollars to pounds is to double it or 1.5 it. It's a lot. And these range from what look like tiny little castles at 2,400 pounds to bigger castles at 3,000 pounds. So there's a range, but they're pretty steep. And we can get a better estimate, possibly, by assuming that there are more flats like the ones that we've observed, effectively trying to derive the population mean from the data we do have. And rather than assuming a distribution, what we're doing here, as you can see, we've repeated some of these apartments just in lots of different orders. We've bootstrapped from our sample with replacement. This kind of data should, in theory, be more closely resembled, should more closely resemble what our true population looks like, rather than make assumptions about what that looks like from our data, just assuming a normal distribution with, the beautiful symmetry and non-platykurtic and all that jazz. So just to remind you what bootstrapping is effectively, is we're going to take a bootstrap. I realize it's circular. Effectively, it's a random sample taken with replacement from our original sample of the same size as the original. So it's like so it's not like it's making new data or we're going back to the population. We are grabbing the individual values repeatedly from our data. And then we are using those to calculate the statistic of interest. Now, this can be a mean, median, proportion, slope, really anything. And we do that a ton of times to create a distribution of that statistic. And then we calculate the bounds of that estimate using our data rather than making assumptions about the distribution and standard errors and all those other things. So this is a very data-driven process. And often it's easier than trying to derive what the distribution of that sampling statistic should look like, or the test statistic from whatever value we're looking at. And so you'll see this a lot in moderated mediation, where there's some messy thing and it's just hard, and there doesn't seem to be an easy, straightforward solution, and that's where bootstrapping is the best, because it doesn't require you to know what your distribution looks like. It just has to have your data. And it goes from there. Now, obviously, it's not a perfect system, but it does pretty well. And a lot of non-parametric stats do pretty well. So how do we do this with tidy models? Well, we're going to specify our variable of interest, in this case, rent. And then we're going to generate 15,000 bootstrapped samples. And we'll do that, as you can see here. There should be a pipe that I'm missing, and I apologize for that. And we're going to generate effectively all the different distributions from 15,000 times. And then we'll calculate the mean for each of those bootstrap samples. And we'll save that resulting, okay, here I've put the pipes back in. And we'll save the resulting bootstrap distribution as its own data frame. And we'll have 15,000 observations of whatever our statistic of interest is. So I'll leave it as an exercise to you to answer what these posed questions are, although I kind of gave one away. Oops. And so let's visualize that. And so here we can see a very lovely histogram that's a little too wide or tall, but they show us what different combinations, and 15,000 combinations of our data look like of means. And it looks pretty normal for the most part. So we probably would have been fine, but it's helpful. And effectively, what we do to calculate a confidence interval is just summarize using quantiles. So the upper and lower limit, we just extract those from our data. So for a 95% confidence interval, we want 0.25% on either side. So we want the 2.5 percentile and the 97.5 percentile. And that gives us our confidence interval around our estimate. And here it is visualized. 95% of our data fall in between those two bars. And anything outside that range is considered unusual. So how do we interpret this? We've got four choices. So the 95% confidence interval for the mean rent of a 3-bedroom flat in Edinburgh was calculated as ranging between 1,600 and 2,200. I'm rounding. Which of the following is a correct interpretation of that interval? 95% of the time, the mean rent of 3-bedroom flats in this sample is between 1,600 and 2,200. 95% of all 3-bedroom flats in Edinburgh have rents between 1,600 and 2,200. We are 95% confident that the mean rent for all bedroom flats, all 3-bedroom flats, is between 1,600 and 2,200. Or D, we are 95% confidence that the mean rent of 3-bedroom flats in this sample is between 1,600 and 2,200. Okay, I'll leave that as an exercise for you. And if you're still unsure after, I'm happy to let you know. But let's cover the last little piece here on accuracy versus precision. So confidence level. We are 95% confident that ... So suppose we took many samples from our original population and built a 95% confidence interval based on each sample. Then about 95% of those intervals would contain the true population parameter. So which of these lines represents which confidence? I'll leave that as an exercise for you. You can probably guess that the broadest, so like the 99th confidence interval, is the widest because it captures 99% of the data. Narrower, smaller confidence interval. So if we want to be really, really certain that we are capturing our population parameter, should we use a wider or narrower interval? What are the drawbacks of using a wider interval? Audience participation? Excellent. Why, thank you, Tuki, for your active participation. He's sleeping. Well, think about it this way with the weather. So take a look at tomorrow's weather. The high temperature will be between 40 degrees below zero and 200 above. It's true. That captures our estimate with like 100% certainty, with like very rare polar vortex exceptions. But is it helpful? Probably not. So how do we get the best of both worlds, where we both have high precision and high accuracy? Well, we can do that by changing our confidence interval. How would you modify this code to get a 90% confidence interval? How would you change that for a 99% confidence interval? I realize that you can't answer because Tuki's asleep. But my point here is that you have to make the decision. The convention in our field in psychology is typically 95 on both ends, but you might only be interested in a one-tailed or two-tailed or one direction or the other. And so being able to actually control and estimate these not even estimate, quantify these estimates is an important skill. So just to recap, a sample statistic is not a population parameter, but if the sample is good, it can be a good estimate. And we report the estimate with a confidence interval, and that the width of this interval depends on the variability of sampling statistics from different samples from our population. Now, since we can't continuously sample from the population because it's expensive and just unwieldy and all those other reasons that we don't repeatedly sample to fulfill the not the law of large numbers, but the central limit theorem. Instead, we bootstrap from one sample that we have to estimate some of our sampling variability, as well as get a sense of what the distribution of our parameter looks like. And we can do this for any sample statistic, including a mean, a median, a mode, you name it. It's possible. And on that note, I'm going to wrap up here and probably not use this puppet again. So I'll see you later. Bye.